In the last video, we looked at how a high-performance computing system might be structured. As part of that, we considered the compute cluster, which represented an important part of the supercomputer that's dedicated to doing large-scale computing. Here, we'll go through how you might specify and execute a compute job on the compute cluster. Like before, using the Owen supercomputer at the Ohio Supercomputer Center, or OSC, as a specific example. We'll focus mainly on Portable Batch System, or PBS software, which, as of fall of 2020, when I put this video together, was the software used by OSC to manage and execute compute jobs. But there are plans for OSC to transition from PBS to the other major job scheduler, Slurm, so we'll also take a look at that one towards the end. First, let's think about what the purpose of software like PBS and Slurm is. Supercomputer resources are large, but they're not unlimited. Since demand for these resources could exceed what's available at any given time, such software provides a framework to manage when and where jobs get run. They consider things like how many processors or cores a given job will need, how long it will run, and how much memory or RAM it'll require. And they prioritize and execute jobs to try to most efficiently utilize the available resources. It's possible to define and submit jobs directly on the command line, but it's much more common to use a job script. And that's what we'll do here. I'll use the Nano text editor to create a script with the code I want to run. If you aren't familiar with Nano, you can check out the video Creating and Editing Text Files at Command Line. Alternatively, you could create this file in any plain text editor on your local computer and then move it to the supercomputer with something like SFTP, which we'll talk about in another video. We'll keep the code simple for now and just write a single make directory command to create a new directory named firstdir and save this file. I'll call it jobscript.sh. If we want to execute the command in this file, one way to do that would be to add executable permissions to the file and run it. I'm doing that here with the change mode or chmod command and its +x argument. Checking the contents of my working directory, I see this file. For me, the green text indicates it is executable. Because it is, I can use // the name of the file, jobscript.sh, to run it. And if I then check the contents of my current directory again, I see the folder firstdir was created, meaning it did run. It's important though to recognize that this was run on the login nodes and not on the compute cluster. Like I mentioned in the last video, small tasks like making a directory are fine on the login nodes, but larger compute jobs can't be run there. So, let's try this again, but run it on the compute cluster. There are two main things we need to do. First, we need to provide the information the scheduling software needs. And second, we need to submit the job request. With PBS, the job information is defined with PBS directives at the top of the script, which I've reopened here to edit. It should be fairly easy to search online for PBS directives and get information on how to specify these. OSC's help includes a page that lists each one. A few are especially important: the wall time, the number of nodes and cores, and also the account the computation will be charged to. We'll specify the wall time first, which is an estimate of how long the job will run. Each directive is identified with a pound or hashtag symbol, followed by PBS at the beginning of the line. The wall time is then specified with the -l argument, which stands for limit, and this is followed with wall time equals and then the wall time you'll set for the run in the form hours, minutes, seconds. Since all we're doing is creating a directory, the actual runtime will be very short, less than a second, so we'll set the wall time for 1 minute. If you're not sure how long something will run, it's better to overestimate than underestimate. The wall time is the amount of time a certain set of processors will be reserved for your analyses, and if the job exceeds that wall time, it'll be aborted before it finishes. The only downside to overestimating is that longer wall time estimates might lead to longer waits for the job to start running, since identifying resources to dedicate to your run becomes more difficult as the length of time and number of processors requested increase. Next, we need to specify how many nodes and cores we want to reserve for the job. Remember, a node is basically a computer, and a core is an individual processor. And the supercomputer we're currently working on consists of 808 standard nodes, each with 28 cores. Again, this is a small task, so a single core from one node will be plenty. This is also set as a limit with the -l flag with nodes equals 1, ppn, which stands for processors per node, also equal to 1. There's a separate -L or limit specification for the amount of RAM required, but by default, a little over 4 gigabytes of RAM is allocated for each core that you request, so we'll just use that default here. Note that if your job does require more RAM, you'll need to specify a corresponding number of cores. For example, if you need 16 gigabytes of RAM, you need to request at least 4 cores, at a little over 4 gigs per core. Finally, when it comes to nodes and cores, there are 28 cores available per standard node on the Owen supercomputer, meaning the maximum number of cores you can request for a single node is 28, but other supercomputers will likely have different setups. If you need more processors than that, or more RAM than the corresponding 128 gigabytes that's shared by the 28 cores on a node, you'll have to take some additional steps that allow you to connect multiple nodes and share memory among them, such as using MPI. In the great majority of cases, though, the resources on a single node are likely to be more than enough for you. The final thing we need to specify is the account to charge the computation to. We do that with a -A argument. I'll use my account PAS1532 and then save the file. Now that I've defined the information the job scheduler needs at the top of the script, all that's left is to send the script to the scheduler. But before I do, I'll go ahead and delete the first dir folder that we created previously, since the goal is to recreate it with this compute job. With PBS, the command to send the job is qsub, which submits it to the job queue where it's held until sufficient resources are available to run it. One thing that's immediately returned is a job ID, which indicates the job has been successfully submitted to the scheduler. We can check its status with the qstat command. Think of this as status of the queue, and it's a good idea to use the -U argument and specify your username so you only see the status of your jobs and not everybody's, as it could be a long list. The column labeled S, which is the second to the last column, gives the status of the job. A Q means it's in the queue and waiting to start. An R means it's running, and a C means the job is complete. Several minutes after the job has completed, it'll be removed from this list. Now that the job I sent is complete, I can check for the folder it was supposed to create. When I list the contents of my working directory, there are 2 new files, one with a .e extension and one with a .o extension, each followed by the job ID number. These respectively store error messages and any output that would have normally been printed to the screen. However, the new folder isn't there. This demonstrates an important feature of runs on the compute cluster. When the job is sent, it's physically being run on a different node, not the login node, and the working directory automatically changes to your home directory to start the run. So the new folder firstdir was created in my home directory and not the directory I sent the job from. There are several ways to handle this, and often there are special variables available that make managing these locations easier. 3 common ones are $home, which stores the path to your home directory, $tempdir, which stores the path to a temporary folder that's created on the compute cluster node specifically for the job and only exists for the duration of the run, and $PBSO workdir, which stores the directory where you sent the job from. I'm going to reopen the script and add a line to first move back into my original directory using the $PBSO workdir variable. I can then submit the script again with the qsub command, and after the run completes, I now see that folder, along with a second set of error and out files associated with the most recent run. Finally, I mentioned Slurm earlier, which is the other major system used for job submission and management. Slurm and PBS work in very similar ways, and the only real practical difference is that the specific commands change. For example, the qsub equivalent in Slurm is sbatch. $PBS will become $slurm, and the Slurm wall time specification is -t instead of wall time equals. A search for something like PBS versus Slurm online will likely provide multiple resources to help you translate the syntax between the two. In upcoming videos, we'll extend the focus on submitting jobs to include running compute tasks in parallel, which really allows you to take advantage of the power of a high-performance compute system.